Greetings, loyal viewers. I apologize in advance as I am sick, so my voice is not quite up to snuff, but I will still attempt to do this very well. This is, as promised, this is how jdupes works. This is how any file duplicate scanner that's worth its salt actually works. This may look a little bit cryptic at first, but I'll go through it, and I think that you'll be pretty confident in your understanding of how these programs actually function once I'm done. So, right off the bat, I want to point you over here to the legend. Each of these are files. All of these squares you see here are files, and they have a file number here at the top. Look at me messing up my paper. They have a file number at the top, partial hash, full hash, we'll get to those later, a size, which is how many bytes the file is, and an inode number, which is basically the number of the file on disk. The inode number, if you don't know what an inode is, it stands for index node. It is originally from old Unix systems, and it's just sort of been carried over. Every modern system works with extent-based files, and every file is actually just one of a massive number of files. And they're all put in a table, and the names and such are just separate parts that point back to a certain numbered file. So, inode number is the actual on-disk number of a file in the file system. If an inode number is the same, then you know that the files are identical, and they're sharing their data area, which means they are automatically, immediately duplicates. There is no way for them not to be. Here, at the start, this is the first phase of duplicate scanning. We load up our files, and we start looking at them. Right now, there are no hashes because we haven't read any file data. This is metadata. This is the information on the file system about the file. These numbers are for convenience, but these numbers are not. On the left, as seen in the legend, we have sizes, and on the right, we have inode numbers. So what you'll notice is, first of all, file 1 and 2 here are size 6. File 3 is size 7. 4, 5, 6, 7 are all 8, and 8, 9 are 11. So we can immediately see during these early checks, which are cheap, computationally these are cheap, we can immediately see that these two and these 4 and these 2, based on their sizes, could be duplicates. But this one, size 7, there are no other files of size 7. For a file to be an exact duplicate, it has to have the same number of bytes. So we immediately discard that. File 3 is gone because it has a unique size. It won't match anything. No matter how many times we compare file 3 to all the other files, it'll always fail this size check. It cannot be a duplicate. So we immediately, before we touch any file data, we look at this size metadata and throw away anything that's got a unique size. Everything else, some duplicate scanners sort things into sized groupings. Some don't. Mine doesn't, but it does use a size comparison to throw things out before it proceeds further. The other thing, if your duplicate scanner understands hard links are where files share the same data area. See, both of these have the same inode number here. That means that they are the same file with just different names on disk. They are linked together in a way that causes them to share the data area. They have to be duplicates. So, right off the bat, these are duplicates and need no further scanning. We don't have to compare this pair in any other way. So for this pair, we go ahead and just mark it as a duplicate pair, and we never do anything to it again because there's no reason to. So we've already eliminated 3 files without reading a single byte of file data. Moving on to the next phase. 7 files remain out of this 9. Actually, I'm sorry, 6 files. File 3 got discarded, and I'm being silly. Partial hash matching. Now, I want you to refer to this diagram right here. Hashing, it's a little complicated, but basically it takes a chunk of data, and it runs through the chunk of data, performing a mathematical function called a one-way function that it just basically takes the data and it calculates a number based on that data that's supposed to represent the data in place of the full data. So a partial hash means that we are hashing here, but we're not hashing the whole file. In jdupes in particular, a partial hash is performed on the first 4 kilobytes because on most drives, almost all drives now, you know, take your pick any hard drive that exists. On most of these, they're what they call advanced format. In fact, you'll see the AF. This is a hard drive, but solid state drives are this way too. The physical sectors are 4 kilobytes, and it emulates the old 512 byte addressing for compatibility reasons. Because of this, partial hashing effectively hashes the first sector of the file, which means if we read the first sector of each of these files, then we're not wasting time running it over the entire file. These files could be kilobytes or they could be gigabytes. If we have a gigabyte file and we can look at the very first part of that and say, wait a minute, it doesn't even match at the start, then we can avoid a lot of work. So partial hashing just checks the very beginning to see if there's differences right off the bat. Because if we can skip that, we know that partial hash mismatch means full file mismatch. Because if we can detect a difference here, we detect a difference everywhere. It doesn't matter. We're looking not for duplicates so much as to find things that can't be duplicates first. Duplicate scanners are really fast filters, fast exclusion machines. So that's what we did here. We found files that have to match, so they get excluded from the rest of the process. We found a file that can never match, so it's excluded. And now we're doing partial hash matching. So each one of these files, first sectors is read and hashed, and these are supposed to be just representatives of the hash number. I didn't want to confuse you with full-size hashes that are huge. It wouldn't fit on the paper anyway. This is a simple explanation. So these numbers represent the data contents at the first 4K of the file. Well, now wait a minute, 74 doesn't match the 19s from these other ones, so this one doesn't have anything in here that it can match with. Oh, get rid of it. Now, we're down to 5 files out of the 9. And how much have we spent? We've read metadata for 9 files, which can be very cheap if they're in the same folder, by the way. We've read file data for 7 files, but only the first sector. Now we're down to 6. 6 is where it gets ugly, okay? I keep saying the number that's at the end. This is 5. Full hash matching reads the entire file. So here, this is expensive. We're going to read the entirety of these files, and we're going to make a number that represents the data contents of those files. But it's not the partial, it's not the first 4K, it's the whole thing. So we make a hash again for the whole contents of these files, and wait a minute. We can compare these numbers because comparing numbers is cheaper than comparing all of the file data. We can compare these numbers and see that, hold on, so these partials matched, but this full is different. So somewhere after the first 4K, there's a difference. So we can throw this file out too. We know it can't match. Now, assuming our hash function isn't a complete POS, we have a set of almost certainly duplicate files. However, you'll notice there is one more step. That one more step is byte-for-byte comparison, which is skippable in jdupes using a special option, but is dangerous for this reason. This is the same thing as hashing, except instead of calculating a hash with the data, we're actually taking the full file data and comparing it against the other file or files. And that's what this is over here. Notice this is different. It came up with the same hash, but it's different. Sorry, I just realized I needed to explain this to you. So with hashes, the problem that causes us to do this last comparison is called the birthday problem, or more generally, the pigeonhole principle. So let's say you have a hash function that produces a number between 0 and 9 or whatever. I actually did this wrong, but this can represent up to 10 values. So please excuse the diagram for being slightly off. Technically, this can represent 10 values, but there's more than 10 numbers in our set. So there is not one unique value of the hash for every single thing in this set. So it goes with most file data. A hash of a certain size can only represent a certain number of bytes before you get duplicates, or hash collisions. So this can represent 10 items uniquely, but there's no way once you get to 11 items for a hash that can represent 10 for there to be no collisions. This is why, as a safety, we do byte-for-byte comparison at the very end. Now, one reason that we could skip this is if the hash function is pretty good, which xxhash64 and jdupes is, if the hash function has very good properties, and because the size also plays a part, so the size sort of adds to the entropy, if you will. We're matching both on size and on hashes, partial and full, whatever. So there's not a lot of room for collisions in practical use. But if a collision occurs and you just delete based on this, well, here's a practical example. You've got these files here, right? And these two don't actually match, but they look like it based on hashes. You know, if you delete one of these files, they have different data. So you've deleted unique data. You have lost data. That's why we do this last comparison. So once you've reached the end of all this work, you have a list of match pairs. You can do with them what you will. They often get chained together. If you have lots of files that match each other in pairs, you can combine the pairs to make a match chain. But the point is, you end up with a set of matching pairs of files, and you can do all kinds of stuff once that's done. You can delete, you can hard link, whatever. But the point is, the vast majority of the work done by a duplicate scanner isn't actually checking for duplication. It's checking for not duplication. Because if something looks like it can't be duplicate, then you get rid of the extra work. So notice by the time we get to byte-for-byte comparison, we're down to 4 files out of 9. So we've dropped 5/9 of the work. That's a lot of extra work that you would be doing if you did a naive scanner that just takes all the files, full hashes them, and uses that to compare the files. That's the most naive implementation you can get of a duplicate scanner that does anything other than just compare files byte for byte directly. A little bit more information. A lot of people over the years have suggested to me, hey, why don't you use XYZ hash algorithm instead of the one that you're using? Well, no, I don't want to do that because it needs to be as fast as possible, more than anything else, because this hash is not used, generally speaking, because of this last comparison. The hash is not used to match files. The hash is used to see that files can't match. Because if files have the same data, they will always hash up the same way. But if files have different data, they may or may not have a hash collision. But files that are identical always do. So we know if there is a difference between the hashes of 2 files of the same size, the data can't be identical because identical data always produces an identical hash. That's why this goes away. Changing the hash from a fast hash to a so-called secure hash will just slow down hashing with no benefit whatsoever. And in fact, I inherited MD5 from fdupes when I forked it. I threw away MD5 at some point for xxhash64. I wrote my own hash we won't bother talking about in the interim. But changing out the hash function for a fast one made the work go a lot faster because we weren't wasting time securely computing something that really doesn't matter that much. Even if your hash has collision problems, the entire process means that it'll still work fine because you're always doing this safety check. So there's no value in using a so-called better hash. What you're really suggesting is using a slower hash for no reason. Anyway, I hope that this has been informative. I didn't want to get too deep into the weeds, so I didn't explain anything beyond just the basic steps of how jdupes does hash, or rather file duplicate scanning, or rather, more importantly, duplicate, non-duplicate exclusion. So this is basically the way it works. And if you have any questions, I want to know down in the comments. Thanks for watching. Take care.